Hey everyone, it's me, Miss B, and in this video we are looking at the Unit 3 Lesson 14 cumulative practice problems and the Unit 3 Lesson 15 cumulative practice problems for illustrative math geometry. So we're going to start here with number 1 from Lesson 14. Just a heads up, this is kind of a long assignment. I do understand it is two homework assignments kind of put together. So there are actually 3 pages of this first assignment for 14. There are 9 questions. And then there are 2 pages that cover Unit 15, or I'm sorry, Unit 3, Lesson 15. There's 7. So there's 16 questions altogether. So it is kind of a long video. I do appreciate your patience, and you can always scroll through to find the question that you're looking for if you're looking for one specifically. So, which of the following are right triangles and show how you know? We are going to use the Pythagorean theorem and just double check everything here. So we are going to check, does 6 squared, which is 36, and my marker is a little too big there, does 36 plus 81 give us 144? And I believe the answer to that is no. But you can always check. I'm going to double check myself on a calculator, but I'm pretty sure this one does not add up. 36 plus 81 makes 117, so not quite. That's what I thought. Now, let's check our next one. Now, yes, I am doing a squared plus b squared equals c squared. The key part here is that it's always the largest side or the longest side that is going to be your hypotenuse. So even though they are not showing me a right triangle with pieces labeled, the biggest number will always be across from the biggest angle. And since you're not going to have more than a 90-degree angle in a right triangle, it's always going to be your hypotenuse. So that's an easy way to tell just from numbers on your paper. So let's check this next one. 8 squared would be 64, and 10 squared is 100. And is that going to equal 13 squared? What's 13 squared again? That is 169. Very close. And it's 6 o'clock. But that is going to make actually 164, not 169. So let's actually cross off A, and we're going to cross off B because B does not work. So we'll try C. This is 9, 12, and 15. I do believe this one works, but we will show you anyways. So 9 squared is 81, 12 squared is 144, and 15 squared I believe is 225, but I'm going to double check myself on that one. Yep, 225. I'm always a little unsure once I get past 12. I generally know 13, 14, and 15 off the top of my head, but I always like to check. And it turns out that yes, these do equal 225 if you add up 81 and 144. So we know that this one works for triangle C. So we're going to say yep and select that one. And then we're still just going to check triangle D. This is 10, 13, and 17. I don't think that this one works, but we'll try it anyways. So let's say 10 squared, this is 100. 13 squared, this is 169. And 17 squared, I definitely don't know off the top of my head, but calculator can help me with that. That is 289. So we're going to check. No, because I can already see if I'm just adding 100 to this, I'm going to have 269, not 289. So this is not equal, just like this one was not equal. And the first one was definitely not equal. So there is only one correct answer for this, and that is C. Now, the nice thing about this triangle is this is a multiple of 3, 4, 5. It's those numbers multiplied by 3. So if you multiplied it by 3, that gives you 9, 12, and 15. And 3, 4, 5 is probably the best well-known Pythagorean triple. They're small numbers, they're all consecutive, and they work to make the Pythagorean theorem true. So on to question 2, because if I keep going at this pace, this is going to be an hour-and-a-half video, and I don't want that for you or for me. So in number 2, in the right triangle ABC, a square is drawn on each of its sides. So ABC, squares drawn, kind of with areas. An altitude CD is drawn to the hypotenuse AB. And extended to the opposite side of the square on FE. So that's what they're talking about right here. They're saying, hey, there's an altitude, but then they're bringing it all the way down to the bottom of this square. So in class, so in the lesson in class, we discussed the observation that Elena observed that a squared is equal to x times c, and b squared is equal to y times c. So my is observing that these statements can be thought of as claims about areas of rectangles. And they're asking which rectangle has the same area as BGHC. So where is BGHC? It's right here. Yep. BGHC. So, sorry, this one is a square, but we want to look for a rectangle that has this same area. Well, this is A. And really it's A times A. Which one has the same area as that? Well, that's going to be the rectangle right here, the smaller of the rectangles. And this one is going to be x by x plus y. So let's name that one. It does have 4 corners to it. I'm going to call it BEKD. Now they're asking for the other piece, which is which one has the same area as ACIJ. So this other square, which is B times B, this one, the one that has the same area of this, is actually going to be this one right here. So this is ADKF. Now, if we actually look at Y, not the letter Y, but I mean, like, what is the reason that those have those letters? A squared is the same as x times c. Well, that was our first question here, a squared. And then this rectangle has the area of x times c. So if a squared is equal to x times c, that means these two areas are the same. And then b squared would be the area of this square, b by b. That was equal to y times c. So y is the width of this one, and then the height is still c. So they do have the same area, they're just using different dimensions of those rectangles. So this is another way that we can actually look at the Pythagorean theorem visually in terms of areas. For question 3, Andre says he can find the length of the third side of a triangle ABC, and it is 5 units. Mai disagrees and thinks that the side length is unknown. Do you agree with either of them, and show or explain your reasoning? I agree with Mai that this is unknown. It is real easy to want to assume that this is a right triangle, but we are not given any angles in this. And if it was a right triangle, then 5 would be the correct one, or the correct measurement, but we don't know that it's a right triangle. So I'm going to say I agree with Mai. Because we do not know if this is a right triangle. Just because we don't know if this is a right triangle. Otherwise, if we knew it was a right triangle, I'd agree with Andre. But that's question 3, really. For question 4, we have a right triangle, ABC, altitude CD, right here, is drawn to the hypotenuse. We want to find 2 triangles which must be similar to A, B, C. So the order matters because they are going from A to B, that's along the hypotenuse, and then down the long leg. So that is the order I want to go in for my other triangles here. So I do have 2 separate triangles. You can think of them as this green one, and we'll do the other one in blue. These are my 2 triangles that I'm going to be naming, and they're going to be similar to the whole triangle, but we have to do that same pattern. We have to go down the hypotenuse, we have to go up the hypotenuse and down the long leg. So for this blue triangle here, hypotenuse is this, and the long leg is here. So if we're naming this, this is going to be C, B, D. So I'm going to say triangle C, B, D. Actually, I'll say triangle A, B, C is similar to CBD, which is also going to be similar to my third triangle, and that's the green one. So we're going to start by going along the hypotenuse from A to C, and then down the long leg to D. So A, C, D is the third one. Okay, so that's the answer. It's those 2 triangles. Those are the ones that are similar. With number 5 in right triangle ABC, altitude CD with length of 6 is drawn to the hypotenuse. So again, we have the 3 similar triangles set up. Our altitude is right here. We also know that AD is 12. So AD, that's this one here, and they've marked it for us along this piece. They want to know what is the length of DB. Well, good for us. They have given us the 2 separate pieces of the hypotenuse and the altitude. That means we can use the geometric mean of these. So if we had the whole hypotenuse, we could use the geometric mean on other legs, but 6 is actually going to be, so this piece here, the altitude, is going to act as the geometric mean between 12 and whatever this other piece is. So what that means is that we would have 6 be across from, like diagonally across our setup. So 6 and 6, like this. So the number that serves as your geometric mean, or the actual value, whether it's a variable, that is the one that appears in your proportion twice. Now the other 2 numbers, it does not matter where I put them, but I am going to call this one 12. Oops. This is going to be 12, and then I'm going to call the other one just dB instead of giving it a variable name. So 12 times the length of dB is going to equal 6 times 6, which is 36. So all we do is divide by 12 on both sides to get rid of 12, and that means that the length of dB is 3. So our answer here is choice B, because of this one. Now on question 6, we have lines BC and DE. They are both vertical. I feel like I've dealt with this sentence in a couple of these homework assignments right in a row, so you may already know this means they are both parallel to each other. So parallel. So now they want to find the length of BD, so that is one separate chunk here, not the entire thing. And I don't have the chunks along this side, so I can't just do like triangle plus its extra chunk compared to triangle and the extra chunk. I actually have to use 3 and 2 in my small triangle, and then 5 on the bigger one with the entire side here. So I am actually going to give this a variable name. I'm going to say that this variable length, or just the name of that length, is going to be x, because that'll help me. I have to do a little bit more of an operation here. So in this case, I am going to be doing small triangle over the corresponding part of the big triangle. And that is the pattern I'm going for in my proportion. It just kind of helps me to set up the small piece versus the one on the big triangle. But the important piece to note is that for this chunk here, all the way across, this one is going to be 3 plus x, or x plus 3, either way. That is the side of the big triangle I need to use. So while small versus big, I can compare 2 to the 5, and that makes sense. 2 over 5. I'm then going to use small triangle has a length of 3, but the big triangle's length, the whole thing, is 3 plus x. But since I did define x as the piece I wanted to find, all we have to do is then solve for x to actually make this work. So when we cross multiply, we just have to take the 2 and distribute it through 3 plus x. That's why I like to write it in parentheses, because if it's more than one term, we do need to distribute. So we are going to have 5 times 3 to make 15, and then 2 times 3 plus x. So this gives us 15, 3 times 2, which is 6, and 2x. So let's subtract 6 from both sides, and then this would give us 9, I believe. And then if we have 2x, when we divide both sides by 2, that would give us that x is 4.5. And so our answer here is 4.5. It is A. And on one of the previous assignments, we actually found the length of the entire thing, and that one was 7.5, so this checks out. It's 3 plus 4.5 would make 7.5. So let's keep going on to 7, 8, and 9. So here's question 7. In right triangle ABC, AC is 5. Looks like they have that labeled for us. Great, because they have 5 right here. BC is 12, so that's this leg, that's 12. And a new triangle is formed by connecting the midpoints. Well, midpoints is maybe important. I'm going to highlight that to remind myself that midpoints are halfway. So they want to know what is the area of some of these. So if it is A, B, and C, they did give us that this is a right angle. So I can use this as my height, and this is my base. So we are going to say that the area is 1/2 the base, which is 12, times the height, which is 5. Now, since this is multiplication, and multiplication is commutative, you can do this in any order. A lot of times I will multiply the 2 whole numbers together and then divide by 2, or multiply by 1/2. But in this case, I actually know what half of 12 is because it's even. So I can say, if I do this in my head, I can say, oh, well, this is now 6 times 5. And I know that this is 30. Then they want to know what is the area of triangle DEC. So DEC is this smaller triangle right here. The height is going to be half of 5, which is 2.5. And the base is going to be half of 12, which is 6. So this is going to be a 6, and this is going to be a 2.5. We're going to use those numbers now in our equation. So area is 1/2 of 6 times 2.5. Well, 6 is still an even number, so I do know what half of 6 is. That means this area is 3 times 2.5. And 3 times 2.5 would be 6, 7.5? Yeah, 7.5. So the area here is 7.5. Now, does the scale factor for the side lengths apply to the area as well? Well, the scale factor for the side lengths basically is 12 turning into 6. Is that the same as 30 turning into 7.5? And the answer to that is no, because one of these scale factors is 1/2 and the other is 1/4, or vice versa. I might have said the reciprocals of them. 12 over 6 would give us 2, and 30, if we divide it by 7.5, actually gives us 4. So no. The scale factor is actually squared here because we apply it to the length and the width and then multiply it together. So it's like saying 1/2 times 12 times 1/2 times 5. So no, it is applied twice. So the scale factor is squared. Okay. Then question 8, we have quadrilaterals Q and P are similar. What is the scale factor of the dilation that takes Q to P? So we're going from here to P. So I need to know what takes me here. I'm going to use corresponding pieces 5 and 4. So 5 and 4, we know it's either going to be 5 over 4 or 4 over 5. If we're going from here to here, this is smaller because we want it to become P. So that's going to be smaller, which means the scale factor has got to be less than 1. So we're going to use 4 over 5 as the scale factor here. So that is answer C. That brings us down to question 9. This is the last one for homework 14, and then we'll do 15. Priya is trying to determine if triangle ADC, so that is this one right here, ADC, is congruent to triangle CBA. She knows that segments AB and DC are congruent. Before I read any further, I am going to make those congruence marks. So AB and DC. Got it. If they don't give those to you, or they don't even give you a picture, you always want to draw it. That way you can also label it and actually see what's going on in addition to reading it. You always want to have as many ways to deal with this question or with your geometric shapes and situations as possible. So she also knows that angles DCA and BAC are congruent. Okay, so let's find DCA. DCA is in this corner, and then she said BAC are congruent, so that's this one. Does she have enough information to determine that the triangles are congruent? Explain your reasoning. So I'm going to say yes. She has enough information because the one piece that she didn't tell us is something we can see ourselves, and that is that this middle segment, AC, is going to be congruent to itself. So that means for triangle DCA here, I have a side, an angle, and a side. And for my other triangle, I have side, angle, and then that same side is counted for both triangles. So we do actually have side, angle, side congruence. So I'm going to say yes. AC is, or segment AC is congruent to segment AC. So the ADC, CBA, sorry, I was just checking to make sure that my letters actually went in the right order. So instead of saying the, so I'm going to say so triangle ADC is congruent to triangle CBA by side angle, side triangle congruence. You can also just write SAS. I just decided I wanted to write the whole thing out this time. So that's that question, and that was all the way back from Unit 2, flashback to triangle congruence. So we're going to flip the page here and get on with with assignment 3-15, so lesson 15. And lesson 15 is mostly about using pieces to find missing things and complete some of the missing segments. So we can use the Pythagorean theorem for this, or we can use proportional relationships, and we're probably going to alternate between using those and using them as techniques to find missing pieces. So starting with question 1, in the right triangles shown, so there are right triangles, the measure of angle ABC is the same as the measure of angle EBD, so they are talking about these two right up here, and if I zoom in on mine, you can see there are little congruence marks in there. Okay, so they're giving us that, and we also know we have right angles. So I have two angles, which means I have triangle similarity. With that being said, they want to know what is the length of side BE. So they are asking, what is the length of this side here on the right? Now, these are right triangles. I do not need to use the Pythagorean theorem, though. We can use proportional relationships because we have angle-angle similarity. So angle, I'm just going to write that little note, angle-angle similarity. So use proportions. And that proportion, I'm going to compare triangle on the left to the triangle on the right. Let's compare corresponding pieces. So I might say 3/2, since these are both the short legs. And then that would be equal to 5/BE. 3/2 equals 5/BE. So that means 3 times BE, or whatever that length is going to equal 10. Divide both by 3. And you would have BE. You could leave it as 10/3. 10/3. Or if we write it as a mixed number, this is going to be 3 1/3. Or 3.3 repeating. It says show my work. I think I've shown my work good enough. So yeah. Now the next one, there is a hint at the bottom of it that says draw and label the triangle. Well, I was already planning to do that and give you that hint, but the paper gives it to you also. In right triangle ABC, angle C is a right angle, okay? So let's draw, I like to draw my right triangles. We'll just draw a straight line there, up vertical, and we'll draw a line here, okay, and here. It's wobbly, but now it's a perfectly right angle triangle. So angle C is the right angle. Got it, that's my right angle. AB is 13 and BC is 5, so I'll just put A here and B here. So they said AB is 13 and BC is 5. Okay, what is the length of AC? Well, since I don't have another triangle to compare it to, I definitely need to use the Pythagorean theorem here. And so I am going to use, let's just call this side, yeah, we'll just call it X. That's easy enough. So if I am using A squared plus B squared equals C squared, because we have two sides and one missing, so we're going to use Pythagorean theorem. Then my two legs are X and 5. These are what we use for A and B, because these are the legs, and C is the hypotenuse. So I'm going to say X squared plus 5 squared equals 13 squared. So x squared plus 25 equals 169. If we subtract 25, then we get that x squared equals 144. Well, I know how to square root 144. If we square root both sides, that means x is 12. So AC, because that's what they asked for, is 12. And that's what I'm going to put a box around for my answer. So if you're ever using variables to define things or make it a little easier, always make sure that you've given the answer in whatever terms they asked for in the question. Because they didn't ask me what's x, I just used that to help me with my arithmetic here. Now for question 3, they have given us this diagram with lines AC and DE being parallel. So AC is this one down here at the bottom, and DE is this one here at the top. Those are parallel, and DC is perpendicular to both. They want to know what is a reasonable estimate for the length of side BE. Well, I have a 4 here and a 5 here, and I know this is a right triangle. So I know that this is going to be a 3. I'm going to put a 3. Now, we want to know the length of side BE, or what's a reasonable estimate. Oh, they gave us a length here. Okay, they said DE is 1. Okay. I was like, why do we not have anything to compare to? We do. I just didn't finish reading here. Because they didn't tell me up here. They did not say the side length of that piece was 1 unit. And my brain just saw like, oh yeah, they told me all of this stuff. But then segment DE has length of 1. I'm just going to highlight that one, I guess, because that is kind of important. That's what's going to allow us to actually do this question. So let's actually do the question. I know I can use Pythagorean theorem to find this, but I also just know it's a Pythagorean triple. But if you were not sure, you could say a squared plus 4 squared equals 5 squared. And you would get 3 as your answer. So if this is 3 and this is 1, that seems to be my scale factor, that 1/3 is my scale factor here. 5 is the hypotenuse. This side is the hypotenuse, so we're going to say that it is 5/3. So scale factor is 1/3. Hypotenuse is 5. So 5/3, because we are multiplying it by that. That is why I'm choosing 5/3. Okay, for number 4, this one says select all of the right triangles and show how you know they're right triangles. We're going to do the same thing of seeing if they work with the Pythagorean theorem. But I also know that 3, 4, and 5 is a Pythagorean triple, right? So 3, 4, 5. This is also any multiple will work. And if you notice, I have 30, 40, and 50 as my top choice. That is actually 10 multiplied by 3, 4, and 5. And this one I guarantee will work. So if you don't trust me, the numbers on this one, 30 times 30 is 900. 40 times 40 is 4 times 4 is 16, so yeah, 1600. And then 5 times 5, well, this is going to be 2500. And those are going to add up to, yeah, each other. Now 1, 1, and 2, if we square these, 1, 1, and then 2 squared is 4. 1 plus 1 is not 4, so it does not work for B. If I have 8, 15, and 17, this one is actually going to work. It seems a little odd, but the numbers here, they work. So 8 squared gives us 64. 15 squared is 225. And 17 squared is 289. And you can check me on this, but 64 plus 225 does equal 289. So C is also a right triangle. I just know that this one is a Pythagorean triple when I see it. It's not always one I can remember off the top of my head if I'm trying to think of Pythagorean triples. Normally I think of 3, 4, 5, and 5, 12, and 13. But there are two other ones that are less common, but definitely pretty easy to use. That other one being 8, 15, 17, and the one right below this, 7, 24, and 25 is also going to work. So let's check those numbers in case you don't believe me. 7 squared is 49. Now 24 squared is 576. And 25 squared is 625. And if you add up 49 and 576, you get 625. So D also works as a set of Pythagorean triples. Or it just makes a right triangle. Now 4, 5, and 6 here is very close to 3, 4, 5, but a multiple means we would multiply by something, not add 1 to each of them. So let's do this one here, and I'll just show you that it does not work. 4 squared is 16, 5 squared is 25, and 6 squared is 36. 16 plus 25 is not going to give you 36. This is actually going to give you 41. So E is not an answer for us here. Okay, we're almost done. I know this video's been long, but I appreciate you hanging in there with me. For number 5, we have 5, 6, and 7 left. So let's get on with number 5. Andre says he can find the length of the third side of a triangle and that it is 13. Well, if this was a right triangle, that would absolutely be true because 5, 12, and 13 is a Pythagorean triple, meaning it's a set of 3 whole numbers that makes a right triangle. But Mai says she disagrees and that the side length is unknown. So who do we agree with? Show or explain our reasoning. Well, like I said, 5, 12, 13 works if this is a right triangle. But if is a very important word in that sentence. So I don't see any right angles here. Do you? I see one that looks like it could be, but nothing is labeled and they didn't tell us anything. So I agree with Mai because we don't know that that's a right angle. Because we do not know whether or not this is a right triangle. For question 6, we have in the right triangle ABC, altitude CD with length of h drawn to the hypotenuse. We also know AD is 8 and DB is 2. What is the value of h? Well, good news for us. This is another geometric mean. So h here is the altitude. The altitude is going to be the piece that is the geometric mean. So that means it's going to be diagonal from itself. We'll just fill in the rest with 8 and with 2. So this means we cross multiply and get h squared. 8 times 2 is 16. And if we square root both sides, that means h is 4. So that's our answer. H is 4. They gave us a quick question there. Number 7 is a bit longer, but I think we can do it. Select the sequence of transformations that would show triangles ABC and AED are similar. And then they gave us the length of AC is 6. So this whole thing right here is 6. It looks to me like the scale factor is going to be 2 or 1/2 if we're going the other direction. But if we're trying to scale this one up 3, I would have to multiply it by 2 to make 6. 2 would have to multiply by 2 to make 4. 4 would have to multiply by 2 to make 8. So they're saying dilate from center A by a scale factor of 2. So if I took it from center A by a scale factor of 2, that's going to blow it up like this. Okay? Then reflect over line AC. Yeah, I would say that works. I'm pretty sure this one is just A, but let's double check all of our other answers and see if they work or not. Dilate from center A by a scale factor of 2. So far, so good. And then rotate 60 degrees around angle A. Yeah, that's not going to work. Definitely not. Translate by directed line segment, then reflect. Nope, they're not the same size, so translation's not going to work. Dilate from center A by a scale factor of 4. You got the scale factor wrong. So it is just A, our first option. And then that means we are done with this assignment because there is nothing left. So thank you for sticking with me through this entire 2 homework assignments. This has been Unit 3, Lessons 14 and Lesson 15 of Illustrative Math Geometry.